In this section, we're going to look at a hypothesis test for comparing two categorical variables. We have the chi-square test, which we can use on two-way tables to compare and see whether or not there's a relationship between the two variables if we're assuming it's a random sample from a larger population. We're also going to talk about the chi-square goodness of fit test, which is slightly different but still uses the chi-square test statistic. So here's an example that I have where we have a large school system, a very large school system, 1,000 students in a college preparatory program that were all going to go to college were randomly selected and asked their intended major. So they had 1,000 students and the information is organized in this table. So we have a two-way table with the two variables. We have gender or sex, male and female, and then our other variable is their intended major, or I grouped them categories here. We have sciences, humanities, arts, business, and other are our options in this table based on the responses from a survey of these 1,000 randomly selected students. So what we looked at in a previous chapter was how to just analyze the two-way tables with marginal distributions and conditional distributions. So if we want to compare what's going on between male and female here, we could do the conditional distributions is what this first problem asks. And then we're going to look at using chi-square to see if this was a random sample, are there differences in the whole population between male and female's selected majors. So we're going to calculate the conditional distributions in proportions of the type of intended major for males and females, make an appropriate graph for comparing these conditional distributions, and in part C, kind of summarize up, are there differences or similarities, and use parts A and B to support that. Okay, so we have our table, our two-way table, which sometimes you have the totals out here, sometimes you don't, but we have our data in the two-way table. And if we look at males, we can ignore the female column for a minute, and we have 200 out of 450 of the males selected science, which works out to be 44%, or 0.44 if you actually wanted the proportion, as the question asked. And then just go down for each of them in the column there for males, dividing by the total of 450 males, and we get that 44% said they were going to major in one of the sciences, 13% one of the humanities, 9% in the arts, 24% business, and 9% other. We can do the same thing for the female column in the table there. Out of the 550 females, 225 said that they were going to major in a science, which was 41%, and then on down the table doing the part out of whole for the percent. So we get 20% for the humanities, 9% for the arts, 15% for business, 15% for other. And when you want to compare conditional distributions, I like to do the segmented bar graphs because you can see them side by side. I made with Excel these two segmented bar graphs where the entire rectangle represents 100% and the height of the bars, or the area of the graph, represents the percent that it's taking up here. So like 41%. See, for the females, the blue area here, the sciences is 41% of the 100%. So it's like a pie chart, but made into a rectangle, so you can do easy side-by-side comparisons. And I wrote a little bit of a summary here, and you can put it in your own words and pick out the important differences. They're pretty close on sciences, both of them. That's the largest. They differ by 3% there, 44% versus 41% in this particular sample. I can see here that the males, less of them chose humanities than the females. So I said females had a higher percentage for humanities and other, a little bit. The other 9% for the males, 15% for the females. And the females had less of this color, which is business. So we see in the data there, 24% of the males versus 15% for the females. So those are some of the differences I pointed out. They're similar in that science was the most popular for both of them, and females had a higher percentage for humanities, and the other category with lower percentage for business. So that's descriptive statistics. I'm telling what happened in this actual data. What we want to do next is say, well, what if this was a random sample, as it said, out of an extremely large population, and we wanted to know, is there a difference between the intended majors that students are going to select based on the sex, male or female? And that's where chi-square is going to come in. So that's what chi-square can do. If you have two categorical variables in a two-way table, chi-square will test the hypothesis that the null hypothesis is that there's no relationship between those two variables. There's no difference in the distribution of the categorical variable of several populations or treatments. Or in other words, your two categories or your two categorical variables in the two-way table, there's no relationship between them. The alternative is that there is. There's some sort of difference in the distributions, meaning there's some sort of relationship between the two variables. And the way it'll work out, we will compare the observed accounts in the two-way table versus the expected counts if the null hypothesis were true. So that's what we're going to talk about next. How would we find these expected counts? So I have a copy of my table again here from this particular survey. And so the null hypothesis is that there's no relationship between sex or gender and the intended major, or that there's no difference between the males and the females on their intended majors. If that's true, then we would expect the same proportions here. Okay? So to find the expected counts, we start by assuming that the null hypothesis is true. So if that's the case, then if we look at the totals here, and just pick on one here to see how it works. If we look at the sciences, there's 425 students out of 1,000 that selected science. So overall, if we ignore gender for a minute, or sex for a minute, about 42.5%, 425 divided by 1,000, 0.425, or 42.5% of those sampled selected science. So if there's no relationship between sex and the intended major, we would expect 42.5% of the males and 42.5% of the females to pick science. So to compute those, we would do 0.425 times 450, the number of males. That comes out to an expected value of 191.25. And of course, you can't have a fourth of a person, but when we do the mathematics with the expected values, we carry out the decimal places for the computation of chi-square that we're going to do. There's 550 females, so we expect 42.5% of them, or 0.425 times 550, which is 233.75. Okay? So a little bit larger expected value than what we have in the table. So that's going to give us our way that we do it. So here's the general formula for the expected values. You get one for each cell. Okay, we have the totals out here, but my table, let's see, is 1, 2, 3, 4, 5 by 2. So we have 10 cells there. We're going to have 10 cells in the expected values. For each of the cells in my 5 by 2 table here, I'm going to get an expected value to go with these, which are the observed values. So if you look at each one, what we did, I tried to explain where it's coming from. The 425 out of 1,000 was giving me the percent out of the whole table, or the proportion out of the whole table that selected science, and then we're multiplying it by the total number of males and then by the total number of females. But ultimately what we're doing is we're doing the row total times the column total. Those two numbers are the row total and the column total, and we're dividing by the table total. So that's our general formula for expected count. Pick a cell. Say you pick the arts here in male, where you have the 40. I would do the row total 90 times the column total 450 divided by 1,000. Again, that's really doing 90 out of 1,000 to get the percent as a decimal and multiplying by 450. But you do row total times column total divided by table total if you have to compute the expected values.